please take it away.
Okay. Yeah. Thanks for attending my talk. I'm Kuang-Chen. This work is done with Shriram, my advisor. He is not here. Imagine you are creating a calculator. So we have a list of buttons. And for each number, we would like to add a callback function that will print that number. And then just to test it out, we will go through the button list and simulate pressing each button. What would you expect this program to produce? Many people might expect to see 0 to 9, but this is wrong. What you will actually see is all 9. Let's consider another case. Say we are presenting a program to a student and ask them what the output is. Please read it and guess what this program will output. In most modern language, B is the correct answer. If a student chooses A, they might have a wrong semantic in their head. That is, they have a misconception. The photo problem is not limited to Python. Go, as shown here, and C# have also had this problem, and they officially document this problem. You can also easily to find Stack Overflow posts about many misconceptions and in many languages. Students also suffer from misconceptions. Students' misconceptions have been consistently found by different researchers at different institutions using different programming languages. And these misconceptions cross languages because they all share a semantic core where variables are lexical in scope, and terms are evaluated eagerly, and binding alias mutable values, such as arrays and objects, by default. And binding do not alias mutable variable, at least by default. And there's always some higher order and first class values, such as function closures or objects. Given that many modern programming languages behave this way, I call this the standard model of language, or SMAL for short. If people do not understand this standard behavior, they will struggle in writing programs and do not have a chance of learning advanced concepts, such as ownership. Unfortunately, people have lots of misconceptions, even within the scope of SMAL. If we care about misconceptions, how do we identify and correct them? My solution is to build a self-paced, interactive tutorial for students. Let me show you how that works. It is called Small Tutor. Here's an example question from the tutor. You don't need to read any details now. I just want to show you the components. This question shows students a program and asks students to predict the program's output by making a choice. Say a student chooses a wrong answer, 0. The tutor will provide targeted feedback to the wrong answer. And the feedback explains the correct answer and try to help students to overcome the misconception. Now I will walk you through each component. I will start with the program part first. What makes a good collection of programs? The first thing I care about is to make sure I cover a diverse range of misconceptions. Reusing questions from existing literature is not enough for this purpose. These questions are all expert-generated, and after becoming an expert, we forget the problem we initially encounter. And we may never have run into certain mistakes. This problem is widely documented as the expert blind spot. One way to overcome this might be to get students involved in the process of generating programs. So I use a system called quizzes to collect student-written program output and explanation for that output. Quizzes does find some interesting program. For example, I'll give you a moment to read the program. This program detects if a student holds a dynamic scope misconception. The variable in is locally defined inside the function and correctly used inside the function, but incorrectly used at the global scope. But quizzes does not always produce good program like this. For example, this program is more like a reading comprehension than testing programming language knowledge. Actually, even the good program is a bit problematic. The usage of arrays is a pure distraction if our goal is to detect scope misconception. And when you have too many irrelevant details in a program, students might be more likely to make random irrelevant mistakes. So in this example, it is probably better to replace the arrays with atomic data, like 42. So we also want to make sure that the programs trigger wrong answers that are tied to semantic misconceptions rather than other mistakes or due to cognitive load. But even if we achieve all of these goals, the programs can still be a little problematic. Let's consider an example program. I will give you a moment to read. Okay, suppose a student say this program produced 0 because in f, x is set to 0. What is the underlying misconception? The first and only thing that initially came to my mind is that those students have an aliasing misconception. They think the parameter x alias the global x, so changing the x inside the function will change that x. However, later on, we found another misconception that would also explain this wrong answer. Some students think there's only one flat environment where all variables reside. So in this program, the later definition of x necessarily overrides the first one. Without knowing what exactly the misconception is, we cannot correct it effectively or provide good follow-up questions. So for every program, we want the property that every wrong answer corresponds to exactly one misconception. That is, I want to make sure that the programs are able to discriminate misconceptions. Before I dive into details about how to achieve this goal, I would like to briefly show you the misconceptions I found. You can find a full list of misconceptions in the paper. For each misconception, I provide a name and a short description, and a program for detecting the misconception, and an empirical distribution of wrong answers. There are a dozen more misconceptions in the paper. It is difficult to discriminate misconceptions when working with this many misconceptions. It is easy to make mistakes. My advisor and I didn't even always agree with each other as co-authors. How do we make sure that each program really is capturing exactly the misconceptions we want? We need a more principled approach. I'm going to describe a technical innovation that helps this process. Recall that misconceptions are wrong semantic in head. We know how to represent semantics using interpreters, so we can represent wrong semantics too. That is, we can take a correct interpreter and break it to match a misconception, and we call this misinterpreter. So each misconception gets its own misinterpreter. To put it differently, a misinterpreter is the definitional interpreter for that misconception. Let me give you a very concrete example on how I use misinterpreters to generate good programs. Let's consider this program again. If we run this program through the reference interpreter and all the misinterpreters I have, we will find that both the call by ref misinterpreter and the flat end misinterpreter produce 0, which indicate that the program cannot discriminate these two misconceptions. And if we change the program by renaming the parameter to y, we can again use misinterpreters to run the program and validate that this program is good enough. Once we make this change, if students pick 0, we now know they don't have the flat end misconception. To recap, in order to find good programs, I use quizzes to get students' insight and myself to clean up the program, and misinterpreters to check that these programs are able to discriminate misconceptions. Now, let me proceed to my second part, the choices. Actually, this part is easy. I ran the program with all the misinterpreters and collect their output. I also insert some random distractors to make sure that I have enough choices. If I have too few choices, students can guess the answer randomly. Now let me proceed to part 3, giving effective feedback. When students make a mistake, you might want to just tell them that they are wrong, or you might just explain the truth by walking through the program, like what each line does. Or you might want to do both. Education research shows that you should do 3 things, actually. You should show your understanding of their misconceptions and do the other things, the other 2 things. This is known as refutation text, and you can learn more about refutation text in many papers. Here I'm just showing one example. Let me give you a concrete example of refutation text that aims at correcting the call by ref misconception. I will give you a moment to read. Okay, let's come back. So our answer to part 3 is refutation text. It has been more than 1 year since we wrote the paper. We have made many improvements since then. The paper's tutor used only a parenthetical language, something I like it. This is no longer the case. Now students can choose their preferred syntax. And when given a program, the tutors will present the program in the chosen syntax and a secondary syntax. I'm hoping these UI updates help to make the point that this knowledge is widely applicable to many programming languages. We are hosting a tutor for free online for anyone who wants to use it. It is also designed to run locally in case you have student data privacy concerns. Oh, sorry. We already have several universities across the world using the small tutor, and we'd love to have you join us. Please talk to me if you are interested, and I'm happy to give you a demo. This ends my talk. Thank you.
Very cool work. So we have plenty of time for questions. Let me start us off. At one point you said that you try to make sure that there isn't content that can lead to like irrelevant mistake, and that sort of, I'm wondering about that. Like what is an irrelevant mistake? I mean, it feels like a student not realizing that that there's a giant array here and its value is actually irrelevant is in some sense a misconception. Oh, okay. How about now? Okay, so to repeat the question, you mentioned irrelevant mistakes, and I'm wondering about that. So it seems to me like a student not realizing that a big array could just be any other value is itself a misconception.
I see. The irrelevant thing that I explicitly want to rule out is like arithmetic mistake. Say you are summing 10 numbers together, and anyone can easily make mistakes like that. And if you have too many variables to check, students can mess one variable with another, and I don't want to care about those kind of mistakes. But for that one, I think that's a very interesting mistakes. Like, does the semantic depends on the nature of that value? Some students will want to think, we prefer to think atomic data behave differently from structures. And we do have questions that detect this kind of differences. Like for some questions, but we would limit the size of arrays so that they don't become too long and become overwhelming. Yeah. Does that answer your question? Okay, great. Next one.
So you talked about that you wanted each example to really only focus on one misconception, right? And in
Yes.
that sense, I guess it also makes sense that there is only one misinterpreter per misconception, right? But oftentimes people might have like multiple misconceptions at the same time.
Yeah.
And so, while there's only one correct interpreter, there's potentially like an infinite or at least an exponential space of misinterpreters.
Yeah.
So how do you deal with that outside of just the realm of like specifically crafted examples?
I see. There's certainly always a risk of having infinitely many misconceptions. So the best we can do is just should try the same material in multiple population and prioritize ourselves to the one that seems to appear everywhere, or that's at least most prevalent. Yeah. I feel like I'm missing some part of your question.
The combinations of the existing ones.
Oh, yes, yes. I actually thought about that. Sometimes misconception can compose and have interesting interaction. I would say that's a work in progress. I have not thought through like how do they like what group of misconceptions are independent of each other and how do they compose. That's a future work and something interesting.
Thank you.
Yeah. Hi. This is really cool. I think it's useful to get the instant feedback, right? Yeah. But kind of my question is, what happens if the student doesn't think that the explanation is actually the problem that they had, right? Like that, to me, I really think would be disconcerting, right? They got it wrong, and maybe this is related to the previous question, right?
Absolutely.
Like, it's like, oh, so what have you observed in terms of the reaction that students have when this explanation isn't making sense relative to what they thought was happening?
Yeah. Yeah, this is indeed, I agree with you that this is relevant to the point that there might be potential other misconception, and other misconception could lead to the same wrong answer. My solution to this problem is actually that after showing the explanation to students can choose between like, this explanation makes sense to me and this does not make sense to me. And if they choose the explanation doesn't make sense to them, they get a text box. Of course, that's optional. They can choose to enter nothing. But if they enter something that indicates other misconception, and we will further investigate by probably making new program that would hopefully detect that misconception.
That makes sense. Yeah. Thanks.
So that'll be our last question. Go ahead.
Okay. So I was curious about the way that you chose to answer the students. When maybe one of the ways that I would try to give feedback to a student I was teaching myself would be that I would try to explain like what I think the student is getting wrong, and then I would tell them, but actually the output of the program would be that. And why do you think that is? Right, so I would ask them to like rebuild their mental model based on the actual output of the program. And what do you think of the efficacy of doing something like that?
I think I have seen research showing that asking students to first explain themselves would help them learn. But when we have too many questions in one system, it might be overwhelming to do that all the time. So probably a more ideal case is to randomly do it, maybe only 10% of all the time. But at this point, I think I'm pretty confident that our questions do detect the misconception we expect to detect. So maybe that's not actually, no. I think I'm mixing things up. Yes, that will help learning, but we don't want to do that too often. And if students see an explanation that does not match their misconception, that would be frustrating, certainly. And I'm not too concerned about that, at least within the scope of my questions.
Right, great, thank you.
You're welcome.
All right, let's thank the speaker again. And